Okay, so in this video, we're going to solve this optimization problem we defined in the previous video. So we're going to find vectors A and B that maximize the covariance between A transpose X and B transpose Y. So in other words, we're going to try and maximize this term A transpose SXYB, and we're going to do that subject to this constraint on the length of the vectors. So we've got the constraint that A transpose SXXA equals 1 and B transpose SYYB equals 1. So first thing we need to do is to prove the proposition from the notes. So that for any matrix Q, we have that the A and the B that maximize A transposed QB subject to the length of A being the length of B equaling 1, that the maximum here of this term is the first singular value of Q. So this is the largest singular value Q, and that the maximum is obtained at A equal to the first left singular vector and B equal to the first right singular vector of Q. Okay. So this is the left and right singular vector of Q. Let's say it's the first. So the one corresponding to sigma 1, the largest singular value. This is what we want to prove, that for any matrix Q, to maximize a quadratic form like this, we do so by setting A equal to the first left singular vector, B equal to the first right singular vector, and the answer we get is the largest singular value of Q. So let's think about proving this. We'll use a similar style of proof to what we used in the previous chapter for principal component analysis. So we're going to set up our objective, which is going to be A transposed QB. And we've got two constraints. Okay, so we're going to add them multiplied by Lagrangian multipliers. So we're going to have lambda 1 minus A transposed A, because we want A to be length 1. And I'm going to divide by 2 here, because it's just going to simplify the math. It doesn't matter, I've just kind of redefined the Lagrange multiplier. Plus another Lagrange multiplier for the other constraint, so let's have lambda 2 over 2, 1 minus B transposed B. So let's differentiate here with respect to everything we're interested in. So the derivative with respect to A is just going to be QB plus, minus, I'm going to get a 2 lambda 1 over 2 A. So 2 is going to cancel. Similarly, let's differentiate with respect to B. And we're going to get Q transposed A minus lambda 2 B. Why do we get Q transposed A here? Well, I've noted here that A transposed Q B just equals B transposed Q transposed A. They're both scalars, so transposing them doesn't change anything. So now it's clear if we differentiate this with respect to B, we get Q transposed A. And if we differentiate with respect to the Lagrange multipliers, we're going to get back our constraints. Okay, so if I differentiate with respect to L1, lambda 1, I'm just going to get back, well, I'm going to half, aren't I? But half 1 minus A transposed A. And what we're going to do now is we're going to set these derivatives equal to 0 in order to find the minima. Okay, so here we're going to get our constraint back. We're going to get A transposed A equals 1. So these are the interesting ones, and I didn't bother writing down the constraint for B. So we've got two equations here. We've got that QB equals lambda 1A, and we've got that Q transposed A equals lambda 2B. So let's multiply this first equation by A transpose, left multiplied by A transpose. That's going to give us that A transposed QB is lambda 1 A transposed A, which is lambda 1. Now let's multiply this equation on the left by B transposed, so we're going to get B transposed Q transposed A equals lambda 2 B transposed B. Now that is 1, so this is lambda 2. And we've just said that A transposed QB is B transposed QA, so hence we find that lambda 1 equals lambda 2. So we've got two equations. Well, this first one, say, gives us that QB, A is QB over lambda. So let's substitute that into here. So we're going to get Q transposed QB equals lambda squared B. So what does that tell us? It tells us that B is an eigenvector with eigenvalue lambda of Q transposed Q. So in other words, if Q has singular value decomposition, you sigma V transposed. So if this is the SVD for Q, well, we know that the eigenvectors of Q transpose Q are the V's, so we must have that B is one of the vectors VI, one of the right singular vectors. B is a right singular vector of Q. Oh, we could do the same thing again. Okay, over here we could, from up here, we note that B is Q transposed A over lambda. So substituting it into here gives that Q transposed A is lambda squared A. So A is an eigenvector of Q transposed, which we know are given by the columns of U. So A must equal to UI, a left singular vector of Q. So all that remains then is to find out which right singular vector and which left singular value vector we need to take A and B to be equal to in order to maximize the objective. So let's go back to our objective. Our objective was A transposed Q B. So we're going to substitute A equal to some left singular vector UI, B equal to some singular vector Vj, where I doesn't need to equal J. We're going to see what we get here. So we're going to get UI transposed Q Vj. Well, let's just substitute the singular value decomposition for Q. So we're going to get UI transposed the sum over K from 1 up to R of sigma K U K V K transposed times V J. So what we're going to get this equal to, this is going to be sigma I if I equals J, and it's going to be 0 otherwise. So A transposed QB is maximized at A equals to U1 and B equal to V1. And in that case, we find that A transposed QB equals sigma 1, the largest singular value. Okay. So what we're going to do now, we're going to let Q be the vector SXX to minus half, so 1 over the square root, or the inverse of the square root of this matrix SXX. These are matrices. So SXX, the power of minus a half, times SXY times SYY, the power of minus a half. And we're going to suppose that this is singular value decomposition, sigma J U J V J transposed, where J goes from 1 up to T, and T is going to be our rank of the matrix Q. Then we're going to claim that A, which is SXX minus a half of U1, B, which is SYY, negative square root, of B1, we're going to claim that these solve the constrained canonical correspondence analysis CCA optimization problem. So just to remind you what that problem was, this problem, okay, that those vectors A and B that I just wrote down maximize the correlation subject to having these constraints imposed. So that they can solve the constrained optimization problem, which was maximize A transpose SXY B subject to A transpose SXX A equals to B transpose SYY B equals 1. Okay, so let's prove this. Well, first of all, let's let A tilde be SXX to the half A. And B tilde is going to be SYY to the half B. Then just note that A tilde transposed A tilde, well, this is A transposed SXX to the half SXX to the half A, and that we know is 1. Similarly, B tilde transpose B equals 1. Now if we rewrite these, if we write that A here is SXX minus a half A tilde, B is, if we rearrange this, we get SYY to minus a half B tilde. Then our objective, A transposed SXY B, becomes A tilde transposed SXX minus a half SXY SYY minus a half B tilde, which you'll notice is A tilde transposed the matrix Q B tilde. So we've converted our problem, our optimization problem, from being this, and just by rewriting in terms of A tilde and B tilde, we converted it to maximize A tilde Q transposed Q B tilde subject to A tilde transposed A tilde equals 1 equals B tilde transposed B tilde. And that is what we just considered in the previous proposition. Okay. We know the solution to this. Let's say we know the optima is achieved at A tilde equal to U1 and B tilde equal to V1. Or then if we convert back to A and B, this says that A is sxx minus a half u1, and that b is syy minus a half v1, as we claimed. Yep, so that was our claim that the solution to this problem was solved at this value of a and this value of b, which is what we've just shown. So just to note here that I've assumed SXY, SSX and SYY as a full rank. So we assumed SXX and SYY are invertible. And we did that in order to write these square root matrices and these inverse square root matrices. But there's a version of CCA that doesn't rely upon this. I just don't want to get into technical detail. So just to finish off then, the maximum of the correlation with respect to A and B here between A transposed X and B transposed Y. So that is just obtained when we substitute in the values for A and B into expression. So we're going to get U1 SXX minus a half SXY. So I've substituted A in here. Then substitute B in here. We're going to get SYY minus a half V1. And you'll see that this is just U1 transpose, sorry, I missed transpose, U1 transpose Q V1, which is sigma 1. So the maximum value of this correlation here is sigma 1, the first singular value of this matrix Q. So just some terminology then. We say that A1 and B1 are the first pair of canonical correlation vectors. So in a similar way to we had the first eigenvector was the first principal component of the data. The first left and right singular vectors here of Q are the first canonical correlation vectors. The variables, eta 1, which is A1 transposed X minus X bar, and let's call the other one psi1, which is B1 transposed Y minus Y bar. These are the first pair of canonical correlation variables. Okay, so they're like the principal component scores. As transformed variables, we had principal component analysis. These are the transformed pair of canonical correlation variables. And finally, we have the sigma 1, which is the correlation between eta 1 and psi 1. This is the first canonical correlation